Yeah, welcome everyone to the fourth week of the course complex analysis. So as usual, we'll recall a little bit what was the topics we covered in this week. So the week started with a definition of harmonic uh, functions, right? Harmonic harmonic functions, and which there we see the Laplace transformation. Last, sorry, which was actually given by del a square by del x square plus del square by del y square. So harmonic functions are those functions from omega, which is subset of complex number you can take, or subset of plane R2, which is open and connected. And the harmonic functions are those functions which are after applying Laplace transform, they become zero function, right? So after this harmonic conjugates, what are these? Basically, if you are given a harmonic function, you want to get another harmonic function such that, okay, right, like this, given you a harmonic function from omega to c, omega to r, we can take from omega to r. Uh, its harmonic conjugate is defined this way, is v from omega to r, such that u plus iv, this function becomes holomorphic, is holomorphic on omega. So this was the conjugate harmonic conjugate. Now after this, we have seen the maximum modulus principle for harmonic functions, and using the maximum modulus for harmonic functions, we shown that for holomorphic functions we have similar maximum principle. Okay, so that was basically we can write it because this is helpful to your exercises. Okay, so maximum modulus principle. Principal. There's mistake. I think it is principal. PL. Okay, so my English is weak, so don't mind if it is wrong. Maximum modulus principle. Okay, so what is this? We have a harmonic function from, let Q be a harmonic function from omega, or directly we could write here omega from omega to r be a harmonic function. Then for any compact subset of omega is subset of complex plane, so it is always that it is open and connected. If it is not open connected, wherever we are taking, we can take, but here it is not necessary to connected. For any compact subset K of omega, we have supremum over z belonging to K of this function u of z. This is equal to supremum of z belonging to boundary of K of u of z. And same thing for infimum. Infimum of z belonging to K, u of z is equal to infimum of z belonging to boundary of K, u of z. And using this similar maximum modulus for holomorphic function was proved. Okay, that is a long proof. We are not going to recall anything, but yeah, that is good to remember. If similarly, or just corollary of this, f from omega to, yeah, it is complex valued function, so we can take, because f is right, because it is holomorphic function, be a holomorphic function. Then what we have, supremum, or it function attains the maximum. First of all, f attains maximum maximum sorry mod f attains maximum value on any compact set, any compact subset, compact subset K, and it is on the boundary, and this maximum max z belonging to K of modulus of f of z, this is equal to maximum of z belonging to boundary of K modulus f of z. So you remember this? Okay, so after this we have seen the definition of curves and then rectifiable curves and some more related results where if we have uh, continuously differentiable curve, then it is rectifiable. Okay, so yeah, that's all we have seen in the class. So let's start with the solution, and whenever necessary we'll recall and we'll without proof assume that whatever is done in the class you remember that. Okay, okay, so let's start with first question. Which of the following functions are harmonic, right? So showing something is harmonic, we see that uh, u is harmonic if del of u is 0 everywhere, okay, on the domain where is, so u is function on complex plane, right? On C, because this is on C. Two questions are functions are having domain complex plane, and then there is some other domain, so we are not going on the given domain. Okay, so let's check with first A. Del u means del square u by del x square plus del square u by del y square. Everywhere when you evaluate z is at z is equal to 0 for every z inside domain, whatever domain, right? So we can calculate this way, or we can guess some analytic function such that this u becomes a real part of that analytic function, or because we know the one result. So just recall that real part of f and imaginary part of f are harmonic function, where f is holomorphic function. Or we should write just when f is holomorphic function, then real part of f and imaginary part of f, they are harmonic functions, right? So e power x, when you see, so first of all let's check. Okay, we'll guess a little bit and then solve it. E power z is written as e power x plus iy, right? So don't just listen to me, you can also interact whenever you wish. Okay, so yeah, e power z can be written like this. When after this we can write it e power x into e power iy, and solving it more, it gives us e power x, and e power iy becomes cos y plus I sin y, right? Cos y plus I sin y, right? Is this correct? E power I y is cos y plus I sin y. Okay, I hope it is correct.
Yes, sir.
Okay, thanks. Yeah, it is correct. So now we two people are verifying this, but it is correct. So you are with me. E power x into cos y. Oh, this appears in the expression, but some extra expression is also coming. Y is coming. So how to get y? So y in terms of z. So when we write z, it is just x plus iy, right? So I just want to get y, and we will add there. So here real part of u, e power z we got, which matches with our actual function. So if we multiply by minus I here, minus iz, it becomes minus ix plus y, right? Now from here y is equal to I, or just uh, okay, this function and e power z, what is real part of them? So a part I'm trying to get what is u, okay? E power z minus iz, what is real part of this? This is just rough work, or you can copy from here. This is exactly e power x cos y and whatever is written, delete, and plus y, right? But remember, this is holomorphic function, and this is a polynomial, which is also holomorphic. In fact, this is entire function. This is holomorphic on whole plane. So its real part will be harmonic function, and imaginary part will be also harmonic function. So this way we got this u is nothing but real part of this function e power z minus ij. So somehow we used the basic tricks. We were looking at this e power x into cos y, and we got that it is a real part of some analytic function, some holomorphic function. Now there is another way to solve this. The other way is this, to check this. We can check this way also, and then some of them will leave if we, I think we have 2 hours. There are not many questions, so we can solve them easily. So the other way is to do this calculation, right? So we have given u is equal to e power x cos y plus y, and if you take del u by del x, means just ux, what you get? Cos y. I'm solving it fastly, and when you differentiate twice, it becomes 0 because it is in terms of y. And now when you take in differentiation with respect to y, what you get? Uy is equal to e power x minus sin y plus 1, and u of y, y. Further, if you do this, you get minus e power x cos y, right? Is there any problem? Why we're not getting 0?
Yes,
Because
sir.
we are
Ux, the first differentiation with respect to x. E power x
oh,
differentiation.
oh sorry, thanks. Uh, this is e power x, right? So then in the second also we get e power x cos y. Now if you add them, uxx plus uyy, you understand the notation what I'm writing. This becomes 0. This is nothing but delta of u. Okay. Okay, so we solved, let's say it is a prime. 2 ways to get a solution of first one, and this is correct. It is harmonic function. Now we are going to check for second. And now here x cube you are saying, and to get x cube you should think about z cube function. But before going that, I think this might be difficult to get the holomorphic function. So we will check this way. The basic definition. We'll use just Laplacian transformation. Part B, we have function u is equal. Sorry, we should write u of xy. U of xy is equal to x cube plus xy. Yes. Now let's see what is ux. 3x square plus y. U differentiation with respect to x again. We get 6x. Okay, I think it is correct. You get some mistakes, you can point out at any time. U of y is equal to just x. When you differentiate with respect to y second time, you just get 0. Now see here, we are not getting the or plus u of y. This is non-zero. This becomes non-zero on omega, which is, see here. This is 0 only on y-axis, right? Only on imaginary axis. That is x is equal to 0, because then the 6x becomes 0. It is non-zero on C. It should be 0 in the given domain, then only we say it is harmonic on that domain. So it is definition is something like domain wise. So in an open set, if this delta Laplacian transformation is 0, then we say that it is harmonic in that domain. But this x-axis, sorry, this imaginary axis is not our domain, so we cannot say it is harmonic or not. Okay. So from here we are clear that it is not harmonic. So part B is incorrect. This is my part. The last statement was wrong. Okay. Now that you understand this, we can go to next step. Look at this once more, and we'll see next part. Okay, so let's see now third part. We have y divided by x square plus y square minus 2x plus 1 on D, and D is this unit disk. So let's write this. Part C, we have uxy is equal to y 1 x square plus y square minus 2x plus 1. Right. So this further can be written as y mod divided by x minus 1 का whole square plus y square. Correct. So if you remember how we write 1 by z, and z is equal to x plus iy. 1 by z is equal to x minus iy divided by x square plus y square. I'm writing two steps together, so let's not write directly. this way. So 1 upon x minus iy, sorry, x plus iy. We are multiplying by conjugate in the numerator and the denominator. What? X minus iy, x minus iy. Then in the numerator we get x minus iy. In the denominator we get x square plus y square, right? So in the denominator we are going to match. In the numerator we'll think about this later, what it is. That is right. So what is in the denominator? X minus 1 whole square. So this is z minus 1. If okay, so here if it was just z minus 1, 1 by z minus 1, we'll thinking about this 1 by z minus 1. If we write this one, so let's do some rough work and we'll come back to this. The question is pretty simple. If you want to apply this way, you can also easily solve this. Okay, so there is no problem in doing that. But we are trying to get that some its conjugate, harmonic conjugate also, maybe the holomorphic function which makes it. So right now I'm doing this way, but you should not do this way. You should simply follow the definition. Because I know that this is harmonic, I have already checked earlier. That is why I'm trying to get what is the holomorphic function whose real part is this. Okay, so checking that is also not difficult, but we are trying here. So when we have z minus 1, let's say this is our rough order. Z minus 1 can written x minus 1 plus iy 1, and then as this we get x minus 1 whole square plus y square in the denominator. In the numerator we get x minus 1 minus iy. Now if we multiply everywhere by minus I, sorry, plus I, what it becomes. So from here it is clear that minus, sorry, plus I by z minus 1. I'm trying to make, okay, no, nothing to multiply. We are clear now. What is our function? That is imaginary part of this harmonic function. So 1 by z minus 1, this is holomorphic on, what is it? It's the domain of holomorphism. Where it is holomorphic, do you know? On C minus 1. This is rational function. Rational functions are holomorphic everywhere except the place where denominator becomes 0. The denominator becomes 0 at 1, so that is why we are deleting 1. But D was our domain here, and D is properly contained here. So this is holomorphic on D, it's clear. Hence, on D, this is holomorphic, and its imaginary part. So its imaginary part is U, minus U. You can take multiply by minus in actual function. Let's say we had 1 minus z here, so that minus iy becomes plus iy, so it doesn't matter. And its imaginary part is our function minus u of xy. And you know when u is harmonic, minus u is also harmonic. When u is harmonic, any alpha is constant, alpha of u is also harmonic. Just because these functions are linear, so these derivatives, if it was alpha u, alpha would have come outside everything because del u is 0. So basically I'm telling you alpha u, when you apply delta operator on it, alpha comes outside. Now since del u is 0, alpha into del u is 0. So minus u is harmonic, implies actually it is in a if and only if u is harmonic. Similarly, because this delta operator Laplacian transformation is, oh sorry, every time I used Laplacian transformation, this is different. Laplacian operator. That's the different term used in another place. We should not use that. Laplacian operator, not transformation operator. Okay, so there's the mistake. Sorry for that. Anyway, by the name you don't know, but you know what is meaning. So meaning is everywhere correct. Whatever I'm telling, that's fine. Yeah. So we have understood that u is imaginary part of some, not some. Actually, it is imaginary part of 1 over 1 minus z. And 1 over 1 minus z, this is a rational function which is holomorphic on D. So this is harmonic. Okay, fine. Yeah. Okay, so now that we saw third part very clearly, let's see what is part 4. So there's one more thing to say, that alpha is, sorry, delta, this operator, Laplacian operator is linear also. If we have u, which is harmonic function, and we have v harmonic function, so u plus v will be also harmonic. Okay, so there's these two properties, delta of u plus v will become delta u plus delta v. So using that, some harmonic function is again harmonic. So we'll use that, and we'll show the part of this, that x by x square plus y square, this is harmonic. And similarly, because this is a symmetric function, if you see symmetric in x and y, so similarly y upon x square plus y square will be harmonic function. So I'm telling that this is correct, and we'll show that x mod d part will show that x divided by x square plus y square u of x. This is harmonic, right? How to do this? So one way is to apply the basic definition and get the answer. Another way is to guess what is the holomorphic function for which this is a real part or imaginary part, whatever, because both real part and imaginary part of holomorphic functions are harmonic. So you already saw that in the denominator we have x square plus y square. Somewhere we did that this calculation. So from here, what is clear? X upon x square plus y square. This is real part of 1 by z. And see the domain, that is very necessary. C minus 0. 0 is not here. So you're not evaluating a 0. So 1 by 0 is out of the context. So this is real part of 1 by z, and 1 by z is holomorphic on C minus 0. That gives us that this is harmonic. And similarly, y upon sorry, actually here it is minus y upon x square plus y square is harmonic because it is imaginary part of 1 by z. Hence minus of y upon x square. And the sum of harmonic is harmonic functions are harmonic. I'm not going to write that, leaving it now. I hope you understand it. Can we go to next question? Okay, so let's see next question. Set of all harmonic functions d is given by x, which are continuous on the boundary of d. Sorry, which is continuous on whole d and its boundary also. In that set, it is continuous. Y denote the set of all continuous functions on boundary. Let us define the restriction map R from x to y. R of f is f restricted to boundary. Restriction of f to del d. Check the boxes which are true statement. Right, now this question is completely depending on maximum modulus principle. So we are going to use that. What is that? When you have a holomorphic function, it's note that this d bar is compact. D bar is compact, so it is not it is closed and bounded. Everything is fine. So from here, at least one thing is clear: if f belong to x, then maximum. Why I'm writing maximum, not supremum? Because it is a closed set, and here we get maximum inside the set. So we are not writing supremum; we are writing maximum. Maximum z belonging to d bar of modulus of f of z. This is equal to maximum of. Why again I'm writing max belonging to del z, because del z is boundary of z, and that is closed subset. And closed subset of a compact subset is again a compact. So whatever maximum of fz will be, it will take value inside that set. Okay. Okay, fine. Now coming to this is the result we are going to use. Yeah, R of f is 0. So I'm coming to party now. R of f is 0. So R of f is equal to 0 implies f is equal to 0. Yes, that is fine. So let's have a little bit conversation about this. Then we'll write the solution. R of f is equal to 0. This means f restricted to d means when you calculate on the boundary restricted to del d, it is 0. So f is 0 on whole boundary. And the maximum modulus principle says that when you take modulus of f, so it takes maximum in the boundary. But in the boundary function is completely 0. So what do you understand? So all the modulus. So one thing is clear that from here, let's write f restricted to del d is equal to 0. This implies this maximum of modulus of f of z, z belonging to boundary of d, this is equal to 0 because everywhere in the boundary fz is 0, right? What is maximum? Mod. It is again 0. But using the result above, it shows that maximum modulus principle implies that maximum of z belonging to d bar of f of z is 0 because these two quantities are equal. Maximum on the boundary, maximum on the whole domain d bar. right? When modulus of fz is 0 everywhere, this shows that fz is 0 everywhere for every z in belong to D bar, and this says that f is 0. So A part is correct. You understand till now? Yeah. So let's see the next part now. Part B. We'll need to show that it is injective. First of all, we'll see that it is injective or not. So most of the time when in case of homomorphisms, the similar case is here. What happens in case of homomorphism? We see group homomorphism or vector space homomorphism or ring homomorphism, anything. The kernels would be trivial. Then homomorphism is 1 1. Here the similar idea is used to show this, that R is injective. So you see this. When R is injective means what? Let so we R of f1 is equal to R of f2, and we need to show f1 is equal to f2, right? How we are going to show? So because these values are equal on the boundary, this shows that f1 minus f2 is equal to 0 on boundary of D, right? So you can write in two ways, either this way or take one more step and write this. After this, f1 restricted to del D is equal to f2 restricted to del D. This after this you write this f1 and minus f2. These functions become 0 on boundary. Now using A part, what we get? f1 minus f2 is equal to 0 on D bar. Whole domain it is 0 now. This implies f1 is equal to f2. Similar situation is this, and I should not recall that ring homomorphisms are 1 1 when kernels are trivial ideals. But the situation is very similar. That is why I told, because there also this condition, first condition, is equivalent to show that R is injective. So here also these two are equivalent. So this is also correct. Any problem here? Okay, so I hope it is fine. We can see next question now, part C. F in X, since F is a holomorphic function on D, we have a maximum on D bar of modulus of F is equal to maximum on the boundary. This is nothing but maximum modulus principle. So this is correct. This is proved in the class. This is what is written here. Right. What about minimum? So it is minimum of fz on d bar. It's saying that minimum is attained also in the boundary. Do you believe in it? So if there is a maximum modulus principle, there should have also been minimum modulus principle. So this is not true. That is why it doesn't appear in the literature. We'll give some counter example. So first of all, I would like to ask if you have counter example. So take some basic f so that you know very well, and then you can calculate minimum. Basic means the best well-known function, which is identity function, fz is equal to z on d bar. This belongs to X because it is holomorphic and continues in the bound, including the boundary. What is mod of F? Maximum of mod of Fz when Z belong to D bar. Sorry, we are talking about minimum here, no? Minimum. That. Modulus of any number is bigger than or equal to 0. So the minimum is 0 because 0 belongs inside D. Right? What is minimum when you take in the boundary? Fz is equal to Z. And mod Z is always 1 in the boundary, right? So these two are not equal. Okay, you understand it? Minimum modulus principle fails. So that is why we don't get a similar theorem for minimum modulus. Okay. So in case of harmonic functions, you're saying supremum also exists. Sorry, supremum is not supremum exists and it is equal in the supremum in the boundary. Infimum also exists, and infimum also that point belongs to boundary. Again, it is for harmonic function, but not for holomorphic function. Right. Now we have any other option here? Yeah, last option. When fz is non-zero for all z inside D, then we have minimum. Then we have minimum modulus maximum. Right. This is fine. E fz is not zero on D, so 1 by fz is holomorphic on D. Is holomorphic on D. One more thing. Do we require this D actually? So this is fz is non-zero, and also it is given that it is continuous, including the boundary. So now my question is this: 1 by fz, is this continuous on D bar or not? You tell me. Or we do not need to. So the proof is like this. Now because it is holomorphic, we'll take maximum of modulus of 1 by f of z. Z belonging to D bar is equal to maximum Z belonging to D bar. So not D bar, it is actually del D of 1 by mod of f of z. These two are equal, but this implies minimum of mod of f of z. Z belonging to boundary of D bar first, and minimum of Z belonging to del D mod f of z. These two are equal. This is the proof of that. The last option is correct. But in the maximum modulus principle, do we really need that this function should be continuous on D closure? Because there is silly mistake in the question that fz should be non-zero for all z belonging to D bar. In D bar also it is not zero. Okay, so modifying the question, this option is correct. So is that really needed or not? If it happens that fz becomes zero on the boundary, there the function is not continuous because it takes value 1 by f takes value infinity. If fz takes value 0, 1 by fz takes infinity value, right? So that is needed. Okay, holomorphic on D bar. Everything fine till now? So this is this step clear? From maximum I'm writing minimum. Next step. You have some positive numbers, let's say 2, 5, 7, 9, something like that, and maximum of inverses of them is minimum of them. Just like 1 by 2 is maximum between 1 by 5, 1 by 7, 1 by 9. I just told some numbers this way. But 2 is minimum. Then if we inverse, take inverse of all of them, all of the positive numbers, the minimum parts become maximum. Maximum parts become minimum. Fine. Understand it by example. Take 2 points, let's say 5 and 7. 7 is bigger, but when you take 1 by 7, it becomes smaller. I'm using that argument. Okay, so I'm not getting any responses from your side. I hope it is fine. Okay, Jayasri is telling yes. Okay, thank you. Yeah, so I'm going to solve the next question. And the next question is, I'm going to solve it in geometrical terms, very geometric. So I hope you also understand it very well, just like me. I'm drawing first. My drawing is getting incorrect. I'm going to draw the set unit disk, which is the domain here. Then we'll apply f. So assume that it is unit disk. When you apply z square, where it goes? It remains at the same place. So applying z, it goes z square of d. The set is again d. There's no change. Fine. But when you add 2, so then you take plus 2. This addition by 2 is also a function which since the disk, so the center was 0. When you take plus 2, what happens? Plus 2 is here. Here it is 1. So every point is sent to 2 meter away, right side. This 0 center, this goes to here. This point goes to here. Everywhere. This point goes to here. So what happens is this. The center becomes 2. What is minimum here? So this goes to here. This is now f of d. you take modulus of fz, what is minimum value? Where it lies? Can you see from the picture? Okay, so this is the minimum value of fz, and what it is? It is 1. So minimum of modulus of f, where z belonging to d unit disk. So this is d only. This set is d. So d bar. This is equal to 1. Now this is one way. We saw the picture and it is clear that the minimum is 1. Can we have another method so that uh, we can understand what is minimum value of this? One thing is that this function is never 0, never takes 0 value on d. Fz is not 0 or any d. So one way of is, so minimum modulus method holds, and it shows that minimum exists. So minimum, so alpha exists. Sorry, from here this much is clear. Alpha exists. What it will be is our main question. We have already seen that this alpha is equal to 1 from picture, but how to justify that it is 1? So one thing is clear: this minimum of modulus of f z belonging to d bar is same as minimum of modulus of f z belonging to del bar. Sorry, del d boundary. Okay, fine. Okay, so you are with me. We can continue. So now, what happens? What are elements here in del d? How they look like? They are just looking like e power I theta, right? So this is nothing but minimum of modulus of f of e power I theta, theta belonging to 0 to 2 pi. I'm just reducing my problem somehow, real, so that I can understand it very clearly. So now I'm going to put the value of f, minimum of theta belonging to 0 to 2 pi. One side it should be open, but no problem. This is nothing but 2 plus e power I theta square, means 2 I theta, the modulus of this, right? So this is the function, z 2 plus z square. Now next we are going to add 2 plus cos theta plus I sin theta. Okay, it is written e power e 2 I theta, so 2 theta will come here. So my fault is here. So in place of theta, it will be 2 theta. So this is modulus of this. Sorry, modulus of this, and we're going to take minimum theta belonging to 0 to 2 pi. And when you take modulus of some x plus iy, it becomes x square plus y square. So minimum of theta belonging to 0 to 2 pi, 2 plus cos 2 theta whole square plus sine square 2 theta. Right now, because everything is what, real numbers, they are positive also, because the first quantity is square, second quantity is also square. So I'm not writing modulus anymore. What can it be? So expand this, you get 4 square. So 2 square is 4. Cos square sine square becomes 1. 2 into 2 means 4 cos 2 theta. So this is the value we are getting, and we are going to take minimum of this. Now what it is giving us? 5, sorry, minimum of theta belonging to 0 to 2 pi, 5 plus 4 cos 2 theta. Right. Now you see this directly. When everything is in positive, only cos 2 theta gives us is changing. And what can it be when it is minimum? When cos 2 theta is minimum, it takes minimum. It is minimum only when cos 2 theta is minimum in 0 to 2 pi. But cos 2 theta in 0 to 2 pi is when minimum cos 2 theta is -1. minimum cos 2 theta is minus 1. Put this value, this will give us, so minimum, this value is minus 1, sorry, plus 1, 5 minus 4, right? So the following, this is just reasoning part. You understand this calculation? Okay, right. So let's see next question. Fine. So now we are seeing the fourth question. It is Mobius transformations. Right. Mobius transformation is also the part missed in the discussion. This is done in this week. So there is unique Mobius transformation fixing 3 points. Or we'll see here. It is Mobius transformation which maps this value, these 3 points to these three distinct points respectively. So we are not going to directly see what t is. Then we'll take modulus of that and calculate the value. We'll see that what is uh, the Mobius transformation which sends -1 to 0, 0 to 1, or these details are pretty longer. I'm writing this way: -1 to 0, 0 to 1, and 1 to infinity is given by. I'm writing directly how it is given. You solve it. -1 is going to 0. So what should be? Z plus 1, because Z plus 1 sends, when you put Z is equal to -1, it becomes 0. Fine. Now 0 is going to 1. So when you put value 0, it is going to 1. So no need to change anything. It works. Z plus 1 is working. Fine. Now 1 is going to infinity. When you put Z is equal to 1, value should be infinite. So now you're putting value Z is equal to 1, you're getting 2. 1 plus 1 is equal to 2. So in the denominator, we have to do something. Putting 1, it gives us 0. So take 1 minus Z in the denominator. What it gives us what we want. You understand? So when you put Z is equal to 0, you're getting 1. So this is fine. When you get Z is equal to -1, you're getting 0. When you're putting Z is equal to 1, it becomes 2 by 0, and it is giving infinity. So this is the S of Z is given by this. There is a method given in the classroom. You can also write it that way. In terms of ABCD, what these ABCDs are, they will be given by this -1, 0, 1. So in general, if A, B, C, it is going to 0, 1, and infinity, then what is the Mobius transformation? It is given by Z minus A divided by B minus A, because till now A is going to 0, and when put Z is equal to B, it becomes B minus A divided by B minus A. So it is going to 1, so fine. And C is going to infinity. That means in the denominator, it should be Z plus C. So when you're putting Z is equal to C, it should become 0 in the denominator, so Z minus C. But you have to make sure that use something that you have to divide here. When putting Z is equal to B, the denominator becomes 1, so there's no problem of anything. So this is the Mobius transformation with these properties. Okay, so now that we have this is, let's say, S1, and one more thing I'm going to write, Mobius transformation which sends 0i 3i 0i 3i to 0, 1, and infinity. This is given by, let's say, S2 of Z. How to write this? Use this trick, this box trick. What it will be is just Z, we send 0 to 0, no problem. I is going to 1, so we have to write modulo I, so that when Z is equal to I, we put, it becomes I mod I, and it is equal to 1, so no problem. Divided by, when putting 3i, it goes to infinity, so Z minus 3i in the denominator. But yeah, again, we have to divide here also. B minus C, which is, what is B here? I minus C is this 3i. So this is nothing but Z modulo I are getting cancelled. So this is just 2 into Z minus 3i. Minus term is appearing here. So now we are going to a little bit verify that it is working or not. When we put Z is equal to 0, we are getting 0. Fine. When we put I in place of Z, we are getting minus I in the numerator. So there's this problem. 2 is n upside. This is 2 is upside minus 2z. So you can solve it. So if there is mistakes, you can point it out. Now I think everything is fine. When you put z is equal to minus, sorry, 3i, the denominator becomes 0, and yeah, it goes to infinity. Right. So now that we have two transformations, and we need to calculate what is t. T is sending -1, 0, 1, 2, 0, I, 3i. So we are going to write t as a composition of s1 and s2. And what is that composition? So first -1, 0, 1, 2. First we are going to apply s1. What happens when you apply s1? -1, 0, 1 goes to 0, 1, and infinity. And now we are going to apply s2 inverse. What happens? 0 goes to s2 inverse. You see this. This is our s2. 0 goes to 0. I goes to, sorry, inverse. We are applying s2 inverse. 1 goes to I, and infinity goes to 3i. So we are writing t is equal to s1 first, then composed with s2 inverse. Okay. Now further, now we put these values, and simply t of z is equal to this. So one thing is to note here that the Mobius transformations, they in the extended complex plane, they are bijections. Okay, they are invertible. So I'm writing s2 inverse, so there is no problem. Okay, so it is bijection, so that we take inverse of it. Yeah. Now we put this s1 of z, what it is, 1 plus z divided by 1 minus z. So s2 inverse 1 plus z by 1 minus z. So s1 is applied on z. Fine. Now we have to apply s2 inverse. But what is s2 inverse? So simply we'll write here. So now I want to ask, so that this interaction should be both ways. What is inverse of s2? S2 of z is given by minus 2z divided by z minus 3i. Then s2 inverse of z, what is this? If you know, you can speak. If you don't know, you just tell me that you don't know. I will explain.
I think z minus 3i by minus 2z, just reciprocal.
Reciprocal of s2? No, that is not. So the product, if you take reciprocal, that doesn't give us inverse of that. Just like identity function का inverse क्या होता है z का? Z ही होता है ना. So 1 by z is not the inverse of z function, because we are not going to multiply. We are going to take composition, and composition should become identity. Okay, fine. I will of course write here. So in the linear algebra, do you say the inverse of this matrix A, B, C, D? What is inverse of this matrix?
D minus C minus D and the A, reciprocal of the opposite.
Is this?
Yes.
Yeah, but one more thing is missing, that 1 by AD minus BC. Right? So in the Mobius transformation, in the definition already it is given that AD minus BC, this is non-zero, so no need to worry about this number. But fine. Now coming to our inverse of S2, what is happening actually? So Mobius transformation can be written this way also. So when you apply, let's say m of z is written like az plus b divided by cz plus d with ad minus bc non-zero. This can be also written as a, b, c, d applied to z and 1. This matrix format of Mobius transformation. This matrix is invertible. That is the condition we need. So now that we got inverse of the matrix, we apply that matrix here, the next. So let's say this matrix is given by a. Then what happens? First you apply m on z, then you apply a on it. So what happens when you apply a into m, or a composition, or a on mz, whatever? Because composition operation is so the bracket exchange is allowed, associative. So anywhere you can put the bracket. What happens? So this matrix A, when you apply this matrix M, this becomes identity. We just remain identity matrix applied to Z and 1 here. What happens here? this becomes Z only. So understand, Z plus 0, 0 plus 1. This is nothing but Z only. So you got the inverse. How is S2 inverse now? This is nothing but minus 3i minus 3i. This is D we put here, and minus B. What is B here? B is plus 0 only. So 0. There's a little mistake when you write D. You are also applying on Z. So there should be a Z minus 3iz plus 0. What happens in the denominator? Minus C. Minus C is 1 here, so minus C is minus 1. Sorry, it becomes minus Z here. And one more thing, plus A. What is A? A is minus 2. That is just like minus 2 here. So you got the S2 inverse. Now put it here, S2 inverse. Right? Minus 3i. In place of Z, we are going to replace this value. 1 plus Z divided by 1 minus Z. So if you know the matrix of S2, matrix of S1, you write matrix multiplication. But I'm writing as a composition, so here also you no need to worry about that. Both will turn out to be same at the end. So in the denominator we have minus Z. In place of Z, we are replacing by this inside value 1 plus Z, 1 minus Z, minus 2. Now we solve it and we'll get this. So 1 minus Z in the denominator, in upper side also, lower side also. So it gets cancelled. So what is remaining? Minus 3i, 1 plus Z here, minus of 1 plus Z, minus 2 of 1 minus Z. Solving for it further, minus 3i, 1 plus Z. So minus 1 here, minus 2 here, we get minus 3. Minus Z here and plus Z here, that get cancelled, right? Plus 2Z, okay, sorry. Plus 2Z minus Z, it becomes Z only. Yeah, so this is, we get the T. Now we have to calculate T of 3 plus 3i. This is what we wanted to calculate. Right, so putting this in place of Z, what we'll get? Minus 3i. So we have to take modulus, we'll take at modulus at 10. 1 plus 3 plus 3i divided by 3 plus 3i minus 3. So it is nothing but 3i in the denominator. In the numerator we have minus 3i. So we can solve it further. What is in the numerator? 3 plus 1, 4. 4 into minus 3, minus 12 I. And the plus I. No, minus 12 I. Now we are going to take modulus of this. So in the numerator and denominator, so hello, am I audible? There was a little problem.
Yes, sir. Audible.
Yes, sir.
Okay, thank you. So for solving it further, you get 3 minus 4i divided by I. You take modulus of numerator and modulus of denominator, you get the square root of 3 square plus 4 square, nothing else. And it is 25 I. So this is the way you get the solution. So there are many steps used. So let me recall it once more for you. So there is unique Mobius transformation which send 3 given points to distinct 3 given points. So first we get this usual thing, given 3 distinct points sending 0, 1, infinity respectively. We get S1. Fine. Now similarly we get S2 which sends 0i, 3i to 0, 1 and infinity. Now that we have two transformation S1 and S2, we can compose and get the Mobius transformation which is T. How we are composing? Here is the explanation for that. We calculated what is S2 inverse. Here is S2 inverse. If S2 is given by this, S2 inverse is given by this. How we calculated this? This is done in the classroom, but for you I have solved it. Look at the matrix representation of Mobius transformation. You can write it like this. Now that you have 2 cross 2 matrix, find the inverse of it. Inverse of this matrix is given above. Now, so what happens? We are applying after M, we are applying A, and we are getting identity. Once we apply identity on it, identity matrix, it gives us identity function. So actually, matrix inverse is the inverse of the Mobius transformation. We did this. So when you take inverse, is some changing some coordinates like T and A, and in the anti-diagonal part you are multiplying by minus. So you did this. Now this part is not appearing in the inverse. Why this is not appearing? It's because if it is multiplying to everywhere, here also, everywhere, and then in this representation, in the numerator also, in the denominator also, the same number appears. So we can cancel it out. So that is why I'm not writing it. While writing the inverse, it is not appearing. Okay, because this part is appearing in the numerator also, denominator also. So after all this, what we did, we put the value, we calculated what is t, and now that we have t here, t is represented by this, we calculated the value of this. Okay, done. Let's see. Now I think this was last question. Oh, sorry, it has only one part and its value is 5. Okay, so coming to uh, okay, so right, now coming to next question. We have two more questions, 5 and 6, then we'll be done for today. Right, so here we have a Mobius transformation given by this. This is true statement. Right. So if you remember, so in the class it was in the extended plane, Mobius transformations are invertible. Fine. So S is a bijective map on extended form. Okay. So S maps real axis onto unit circle. Let's see where it maps real axis. When we take real value of Z, what it becomes? If Z is purely real or just real, because it is complex number, we are just considering when it is purely real, what happens? I plus x, Z is equal to x plus I1, y is equal to 0. In this case, so only x appears. Sorry, I minus x divided by I plus x. And we take modulus of this. And what it is? It is uh, x plus I, we have to divide and multiply by x minus I. What it becomes? X square plus 1, or directly you can write from here. Actually, what is modulus of upper side? X square plus 1 is inside square root. And then in the denominator, same thing. Minus x square and plus x square, they're same. So x square plus 1, and it is 1. So one thing is clear, that f of this was modulus of f of z. F of real number, this is contained inside unit circle. Why? Because f of z come out is 1, and those numbers which are modulus 1, the set is called circle, unit circle. It's represented by S1, unit circle. It is z inside C, such that mod z is 1. One thing is clear, that real line is maps to circle, but onto is this, that is we need to verify. So showing that it is not onto, it is enough that there is one point inside circle which is not in the image. Its pre-image is empty. Okay, so for what x, fx is equal to minus 1. Minus 1 belongs to S1. We are saying for what x inside R, fx is minus 1. This is your question. From here, what we conclude? The question is modified in another way. I minus x, I plus x is equal to minus 1. This further is implying I minus x is equal to minus I minus x. And this implies that I to I minus x cancelled from both sides is equal to 0. And this is contradiction. This implies that for no x, this condition holds. Means minus 1 belongs to S1, but minus 1 does not belong to f of R. So f is not onto. If you have doubts, you can ask. So this part is tricky. I got a point which does not has premise. Is that tricky? Which point you will take? This is the first case. I found it. I give one counter example. A general proof for this is, if you can't show, you try to disprove. This is the question. When mathematicians has been asked the questions, either you prove it or disprove it. Okay. So proving this was difficult. So looking for a counter example easily gives us that it is not onto. Fine. If you understand this counter example, particular counter example, let me know yes or no. Okay, so F is not onto, so first option is incorrect. I'm assuming that you are also understanding it. Now the next part is S maps the region upper half plane. Imaginary part positive means upper half plane of the complex plane maps onto outside of the unit disk. This is complement of unit disk. This is complement of unit disk. Closed unit disk. Uh, Close. Okay. So now we are in part B, and we are looking for upper half plane. Let me represent it by H. H represents Z in C, such that imaginary part of Z is positive. So the question is F of H is equal to D closure complement. So this is the question. Is this true? And let's see what happens when I means imaginary part is positive. What happens when you take modulus of F of H? Let's say Z belong to H. We are going to take modulus of F of Z. What it is? I minus Z divided by I plus Z modulus of this. And from here we can write it this way. Not every time we should write Z because Z is variable and we are picking some particular Z. So this time this Z is fixed. Let Z belongs to H. Okay, so writing more clearly, X minus X plus IY divided by I plus X plus IY, not with, so Z is equal to X plus IY. Belonging to S means Y is positive. So solving it further, we have got minus X uh, minus I. So we are taking common I. So plus I we are taking common. So we are getting 1 minus Y. In the denominator, X plus I, 1 plus I, 1 plus Y, sorry. Fine. Now what? When we take modulus in the numerator, it becomes right. So in the numerator, we are getting x square plus 1 minus y or y minus 1 whole square, no problem. In the denominator, we are getting x square plus y plus 1 whole square with y greater than or equal to 0. Now you tell me, in numerator is bigger or denominator is bigger? Which one is bigger? Hello, Hemlata. Okay, I'm saying that numerator is always smaller than the denominator. Is this fine?
Yes, sir.
Why? Because you just expand y minus 1 to the whole square, it becomes y
X
square
square,
plus 1.
x square plus y square minus 2y plus the
Yes, that
denominator.
minus 2y part is making it smaller. Right?
Smaller, yes. Yes, sir.
Yeah. So this is always less than or equal to 1. So because y is strictly positive, I'm saying this is strictly less than 1. And this shows that whatever you take Z inside H, what happens? F of H is F of H. This is contained inside the unit disk. So how can it be equal to its complement, closed and complement? So what the whole upper half plane is going inside unit disk, right? Because we're taking modulus of them, they're smaller than 1. F of H is contained inside unit disk. Fine. So this is wrong. So the part B, which was saying that uh, upper plane is going to, this is H, and this is the complement of unit disclosure. This is wrong. Now similar question is part C. So now the question is onto. One thing is clear that upper plane is going to where? Inside unit disk. Is this onto also? So the question is part C is f of H is equal to D. How to do this? So one thing is clear, Fh is contained inside D. Showing that two sets are equal. So other containment we have to solve, right? So pick something inside Z. Let D. Let W belongs to D, and we want to show it belongs to Fh or not. We'll think about this. So from here it is clear. This mod W is equal to 1. No problem. Is this equal to sum of H? We want to see. W is equal to, let's say, f of Z. थोड़ी देर के लिए मान लेते हैं, लेट अज्यूम दैट देयर एग्जिस्ट सम z, and if we get some contradiction it is fine. If we don't get any contradiction, the same calculation will go step back, one step back, we'll come to this situation that we get some z which is going to w. So let's see, w is equal to f of z. F of z is equal to I minus z by I plus z. Sorry. And we only know that mod of w is less, sorry, equal to 1, not equal to 1. My fault. Less than, stick less than 1. Right. So let's say solve it further. W I plus z is equal to I minus z. So solving it further, Wi plus Zw is equal to I minus z. So further, uh, Wi minus I is equal to minus z minus Zw. Minus 1, multiply both sides, take z common, then z. Here becomes 1 plus w, minus 1 multiplying this becomes I minus, take I common also, so 1 minus w. So if there is any wrong calculation, you can point it out, okay? Because I'm not solved it earlier. Right now I'm solving with you. So z is equal to I into 1 plus minus w by 1 plus w. So only this much we have got. And we somehow want to show that z is inside h, inside upper half plane. So to see that, we want to see imaginary part of z, positive. So the question is this, is imaginary part, so directly you can write imz is positive. Let's see if it is or not. What is imz, imaginary part of z? This is real part of I, sorry, now I is gone. This is real part of 1 minus w divided by 1 plus w, right? Now, now we somehow we have to show this real part is positive, but how? So we are going to do a little trick here. Uh, so in multiplying 1 plus w bar in the numerator and denominator makes denominator actually real. So 1 minus w by 1 plus w, 1 plus w whole bar. It is equal to 1 plus w square, modulus of 1 plus w whole square in the numerator 1 minus w square. Sorry, we are multiplying by bar. So we have to write everything fine. 1 minus w minus plus w bar minus w bar. Fine. If you are doubt, you can ask me. 1 minus w bar is mod w square divided by 1 plus w square. This is completely real. So this belongs to real part. So the left part we are looking at, minus w bar, this by 1 plus w square. So is this imaginary? Do you see? W plus minus w bar is what? Completely imaginary or zero? Either that will become zero or completely imaginary. Just like we see here, little calculation. X plus iy, it is w. W bar is x minus iy. So what happens when you take w minus w bar or w bar minus w, whatever you take, x cancelled out from both sides. So either it becomes, so in this case here it becomes I to y, completely imaginary. So this part is imaginary and this part is real. So one thing is clear, that this imaginary part of z, which is uh, real part of 1 minus w by 1 plus w, this, which is also equal to 1 minus mod w square divided by 1 plus w square. This is positive. Why? Since mod w is less than 1 and mod w square is also less than 1. So 1 minus mod w square is positive. So you understand till now what happens? I thought there was some z, f of z is equal to w. Then we have seen that yeah, there exists a z with imaginary part positive. So this implies there exists z inside H that is imaginary part of z positive such that f of z is equal to w. Done. So this is onto function. So this option is correct. You understand? If you don't understand, this PDF will be available to website. You can check it once more. Right. Now that you understand this, we can see the next part. We still have 10 minutes so that we can completely finish. S maps closed unit is to itself. Then modulus of z is less than or equal to 1. Modulus of f of z is also less than or equal to 1. One more thing. Is f an entire function? No. Why? At z is equal to minus I, f. So S is not holomorphic. So we have the option. Let's give time to think about this. When modulus of z is less than or equal to 1, we have to show modulus of s of z for the option. Modulus of s of z. So mod z is equal to 1 is less than or equal to 1 is given using this. We have to show this is less than or equal to 1. Is this correct or not? First, let's check. So I minus z divided by I plus z. We take modulus of this. What are we getting? Sorry, I minus z, I plus z. Let's explicitly write mod z is less than or equal to 1. This implies x square plus y square is less than or equal to 1. So here, solving for this, we get minus x plus I 1 minus y. In the denominator, x plus I 1 plus y. Modulus of this. And this is nothing but x square plus y minus 1 whole square divided by x square plus y plus 1 whole square. We only know this part, that x square plus y square is less than or equal to 1. And x and y both are less than 1. So just to be clear, modulus of this. We can use this x square plus y square plus 1 minus 2y, x square plus y square plus 1 plus 2y. So it seems when y is equal to y is negative, there's some problem. Do you see here? So what happened when y was positive in the previous calculation? When y was positive, where? Yes. When you were showing this, y was positive. What happened? This same value was less than 1. So we think that there will be some problem, and we want to find some counterexample so that a subject is has modulus bigger than 1. What we can take? Let's say y is equal to minus I. That becomes 0. Y is equal to something else, minus I by 2. Very sad. Do you see why? Just because, see, now everything is clear from the picture. S of minus I is what? Infinity. And S is, sorry, S only. S is, everywhere else it is holomorphic or continuous. Continuous. So when you approach towards minus I, just 1 plus I by n. With this way, you have to approach minus I within the domain. You have this unit disk, minus I is here. You get a sequence from this way, where you calculate f of zn. Let's say this is zn sequence, and you calculate s of zn. This will tend towards infinity, towards very big number, because s of minus I is infinity. So s of z is not contained inside. This is wrong. Yeah. Now, do you know this curve? This is famous curve. Cos t sin t is the unit circle. It's representing unit circle when t is running from 0 to 2 pi, but t is running in 0 to 1. So what is our actually curve? Curve is actually this. Starting from here, going this way, stop somewhere here. This is gamma of 0, and this is gamma of 1. Now, is gamma rectifiable? Is gamma continuously differentiable? This is correct. Continuously differentiable means what? Cos t and sin t are basically infinitely differentiable. So twice differentiable तो होगा ही, right? Once it is continuously different, it is rectifiable also. One is also correct. This is done in the classroom. Continuously differentiable है तो rectifiable हो गया. Fine. Now, mod gamma is 1, where mod gamma is arc length of curve gamma. So this is the little bit calculation. We see this. See, when mod gamma is calculated this way, 0 to 1, modulus of gamma prime t dt. So what is it? This actually 0 to 1. Gamma prime t will be cos t is minus sin t, and sin t is cos t. This is gamma prime t, and we have to take modulus of this dt. You take modulus of t, what it becomes? Sin square t plus cos square t, and then we have to take a square root that we're not worried about because it is 1. 0 to 1 dt. This is nothing but 0 to 1 dt, and this is, tell me, this is 1. So mod gamma means arc length is just 1. This is also correct. Gamma prime is not a rectifiable curve. No, right? Because that is also continuously differentiable. So gamma prime is what? This curve. Gamma prime t is minus sin t cos t. This is also continuously differentiable. Same logic. Sin and cos are infinitely differentiable. So here gamma prime is rectifiable also. So this is wrong. This because of not. Fine. Now what about last option? Gamma tilde is a curve from 0 to 2 pi given by same equation. Is this a continuous reparameterization of phi? Sorry, gamma. Not really. Why? What happens to this curve? This curve starts at, let me change the color. It starts at the same point, but this way, it is going to hold up to same point. So a starting point and ending point are same. They are of course representing different curves. So this curve is unit circle, and this curve is gamma is maybe some arc of unit circle. They are different curves. If it was if it was a representation, sorry, reparameterization, they represent same curve. So remember that. So that gives us the solution that yeah, this is a wrong option. Okay, it is clear from the picture, but you can, if you want to write it, you just write it. Ending point and starting point does not match. Gamma tilde has ending point different than gamma. So this way you can write it. What happens? Minus I by 2. Let's do this. Okay. S of minus I by 2. Where it goes? I minus I by 2 divided by I minus I by 2. What happens? This is in the denominator it is I by 2. In the numerator it is 3 I by 2. Sorry. So what it is? Just 3. So S does not map D, which is unit disk, into D closure. Because see, we got 1 point since minus I by 2 belongs to D closure, and S of minus I by 2, which is 3, does not belong to D closure. So we did it. We doesn't